Yes. Okay. Can you hear? One thousand, 2,000, 3,000, 4,000, 5,000. Can you hear? Good. 6 seconds. About 6 second delay. Okay. So today we will cover. Okay. Before I start the lecture, let you know that we already upload the project and the general information. Project 1 and Project 2 is already available in NTU Learn. You can go and take a look. Maybe I quickly scan through the things. No. This one. Yeah. So, yeah, each project is 15%. Just confirm it's week 4 or week 5. Depend whether your group is odd week or even week. Yeah. So the first week, I would say quite important because you need to form the group and find the teammate. So please make sure come on time. Yeah. Trying to meet your friend and then group it. Each group is about 4 to 5 members. Whether it's 4 or 5, the decision is made by the lab supervisor. You can form the group by yourself, but whether it's 4 member or 5 member, the decision is made by the lab supervisor because we need to see the class size to decide the number of group of 4 and group of 5. Yep, case by case basis. So the final decision is made by the lab supervisor. So yeah. So the assessment will be the presentation and the report. And we will base on your algorithm design, the analysis, as well as your presentation and the report, these 4 components to decide your grade for each project. Then each project is 15% of your final grade. Okay. So design-wise, I mean, if you're talking about implementation, you can use any programming language, Python, Java, C++, C, or you are free to use it. Yeah, but just take notes that we just wouldn't allow you, you can use it. If you use any library, online resource, or whatever software, you can use it. But you need to declare. You need to put in your report, declare that you are using certain software, certain library, because those part is not your work. It's not your contribution. You just apply. You just call some people function. Yeah, it's not implement by your own. So this part they will consider. Yeah. Not your contribution. They only know that you use it only. Okay, that is the part the lab supervisor will consider. Yeah, he won't consider you trying to use some commercial software, very expensive, very powerful system, but not done by you yourself. This kind of thing, they won't count it as your part of your assessment. Okay, because it's not done by you. Analysis, of course, we not consider. Okay, this part you need to take notes. We don't consider the state-of-the-art work because definitely within such a short period of time and your capability, you may not be able to compete with the state-of-the-art work. Yeah, but we will just compare your effort, your implementation, your analytical skill, and the experiment you conduct. Okay, you can use any existing algorithm to solve the problem, but if it's someone already published their work there, you just reuse their idea. You have to cite their work, have to indicate clearly in your report. You cannot assume that is your idea. If you claim that is your own idea, and we caught you that this idea is copied from somewhere, then we will penalize you. But if you cite it, you already declare this work. I'm refer this person, that research group, or whatever team doing. Okay, then we know that is not your own work. Then we won't penalize that case. Of course, if you copy from your friends, then that is considered plagiarism. If you take idea from other people, any research group work, okay, then that is not considered plagiarism. As long as you cite it, state clearly in your report saying that this work is referred to this person work. Okay, yeah, you got the reference there. It is fine. Of course, we understand that you won't be overnight, not everyone can overnight think out a great new algorithm. Yeah. Like I said, you need to cite it. You have to cite it. And it should not be, in the end, in your report, everything is exactly the same. Although, because if you just use other people's idea, you just use the idea only. So how you apply it, how you evaluate the things and so on and so forth, the experiment you conduct, the method you use, a lot of things should not be exactly the same. Yeah. So it can be, you can have some people maybe, but you need to cite it. Other group maybe also use the same work, is fine. But it cannot be exactly the whole report, everything we can see that exactly copy and paste, every sentence is look exactly the same. The code, everything, every single line we look at it is exactly the same. Then that is obviously plagiarism. Yeah. But if you just said you cite this person work, he also cite this person work, that is fine. Yeah. It's normal. In practice, we also trying to cite other people's work, it's normal. Yeah. There's nothing wrong to do that. That's not considered plagiarism. But if you copy directly people work, without changing a single things, anything, you just reproduce exactly the same thing, that obviously is a plagiarism. Yeah, so this need to take notes. Because evaluation is based on the correctness, the originality of your proposal. And if you reference, any reference, because even you use the other people work, you may introduce some experiment which they didn't do, you trying to do it, that is fine. Maybe you use different data, that also fine, right? So like I said, evaluation will consider is like the correctness and the work you have conduct, the experiment work, all this, you design some experiment to evaluate analyze the algorithm. All this is part of it's not just one thing, one algorithm decide your whole grade. Even you have the good idea, but you evaluate it, you analyze it poorly, or you present it poorly, you present it is 20%, report is another 20%. All this will be the factor affect your final result. It's not just simply one idea decide it. So you can use the existing idea, it's nothing wrong. Okay. Of course, I also encourage you come up some new idea by your own. That is also fine. So definitely as a lab supervisor, you cannot avoid they trying to compare the group, the work among the group. But we trying not to do it too competitive. But this is unavoidable. Because group 1 present well, then the group 2 coming in and present very badly, we cannot say that they are about the same. That is not fair to the group 1. Okay. So each group only have 10 minutes to do the presentation. So take notes, you have to fully utilize your 10 minutes presentation and highlight the significant novelty. You may not need to present every single thing. You also don't need to everyone to come out and show the presentation. You need to think how to use these 10 minutes to convince your lab supervisor and let him know what you have done and what is your main contribution in this particular work. Okay. Yes. So there's no template, but it's 5 pages. Report, I think somewhere I already said it's 5 pages, including cover page, including whatever. Don't give me all kind of funny excuse saying that you can go for 6 pages and 7 pages. For me, very simple. I only read up to page. I open the file, read from the page 1 to the page 5, then stop. If your conclusion is in the page 6, that is your business. I will consider no conclusion in this report. Okay. So report-wise, we don't have any particular format, but please make sure you got the project title, your group name in the report, of course. Yeah, a lot of time a report no name, no title, nothing at all. Yeah, just full of the work. That is not a good report. Otherwise, we don't have any particular instruction for that. Yeah. But take note that plagiarism is very serious academic offense. Yeah, I have to remind you. It's quite easy to find out because only 5 pages. If it's copy from each other, it's very easy to figure out. Yeah, and you need to submit the code and make sure well documented. And that's mean in short, your lab supervisor can reproduce the result and validate the correctness, whatever you claim in the presentation and the report. Yeah, so all this you need to consider. Yeah, you need to think carefully how to present, how to submit the code properly. Don't just dump in all the code and then not working all through it and ask the lab supervisor to figure out which one they want. That will end out that they will just ignore this thing and consider, if they don't believe your claim in the report and the presentation, they will just penalize you directly. Yeah, according the question already said up to 2 for my part. Yeah, you read the later I show you the project one. So let's submission. Roughly this is the thing. Yeah. Anything I need to highlight? No more. So project one, okay, is trying to let you to do the sequential search. Yeah, for searching the query sequence. Okay, for DNA sequence searching. Okay. Detail I left you. I don't have so much time to go to the details. So basically, you can go and get this virus sequence. You can be any sequence. Yeah, there are a lot of this kind of sequence in in this. You can go to this website to get the details how to download the sequence. Yeah, the data can be from few kilobyte to few gigabyte, so can be a very huge data. And you need to implement the brute force one, as well as propose up to 2. I mentioned that. Where is it? So, up to 2. I did mention that. Here. I think state of the art, any algorithm student. Yeah. I did mention that there's up to 2. You just need to propose up to 2 algorithm. I do mention it somewhere. Let me find. However, is it on top? I think it's here. Yes, I recall in this project. Yes, then you need to propose up to 2 other algorithm. Okay, so you only can propose up to 2. Don't give me 100 algorithm. Yeah, and ask me to select. We only consider up to 2. In fact, if you have a one good algorithm to improve the brute force searching, that also fine. We look at not just the number of algorithm, it's the how you analyze the algorithm and the experiment you conduct, how you prove your idea is good, and so on and so forth, and your presentation, because it's also don't forget it's 4 to 5 member work. It should not be one person. You expect one man work can do well. Definitely that's not the case. You can refer how to form the group. The details actually is inside. So go back and download this too far and take a look. So okay, I don't want to waste the time. I already spent 10 to 15 minutes on this. Okay, if you have any query, you can just send me an email regarding on this project 1. If you want to ask about project 2, please send to Dr. Kerr for more details. If you have any doubt, or you check with your lab supervisor during the lab session. That will be even better. Because they are the one assess your work. Yes, improvement is referred to improvement over the brute force algorithm. That's why I keep emphasizing that the state of the art is not the key. We don't use the baseline. That's mean the baseline is the brute force searching algorithm. You don't propose something even worse than that. I would say very unlikely. Yeah, you want to make propose some algorithm worse than that, you should know that that is definitely not a good algorithm already. Yeah, because brute force one is the worst one. Okay, so that's about the project. So we should move back to the lecture. So today, I still carry on what we stopped last week about the recursive function, this Fibonacci one. Maybe I trying to do the other way to explain this. So if you look at this algorithm, if I have this, maybe not so good. No, don't want this. Let me see whether I can switch on. Okay. So if you look at this algorithm, Fibonacci algorithm, your input is n. So if your n is less than 1, and if your n is equal to 1 or 2, how many function call are there? So it's very clear that it's only one function call, right? So if your function call, if your f, don't know whether it's work or not. So if I have a if f1, you only one function call, because you just need to go into here, then finish, then return 1. That's all. Only one function call. When f equal to 2, it's also the same scenario. But when f equal to 3, if my f equal to 3, then you expect that they will run this line 4, and then they will do 2 function call, recursive call, one for f2, n minus 1. So f2 and f1. Not surprising, these two will just go in and then return 1. So total, when n equal to 3, you got 3 function call in the whole process. Okay, but when your Fibonacci, your n equal to 4, how many function call are there? You will call recursive call f3 and recursive call f2, f3, f2 you won't do anything further, just simply return 1. Then f3 you do f2 and f1 recursive call. Then this one and this one will f2 and f1 will return 1, and then to f3 will return 2 to f4. f4 will get the final answer, which is 1, 1, 2, 3 So but the number of function call, 1 function call, 2 function call, 3 function call, 4 function call, and 5 function call. So total there are 5 function call when n equal to 4. So now my question is, I give you what is the given the n, then how many function call are there? You need to find out. Then you trying to do this, and just like last week we mentioned, you keep doing this thing. You find that you're trying to derive the Wn, because each call you have 1 function call plus the recursive function n minus 1 and recursive function n minus 2. You will find that you're doing this, you through the method of backward substitution or method of forward substitution, you won't be able to get the exact solution. So that's why the next step, I believe that if you search some online, they're trying to tell you that this is the way, but it's not true. It's just an approximation solution. Because the first step, they make the assume that this one and this one is about the same, but it's not true. Because these two, when the n is getting bigger and bigger, the difference is very large. Yeah, you're not really good. I'm not saying that they are totally wrong, but this approximation solution is just an approximation, not the exact one. Yeah, you still can try to do this thing to practice your backward substitution method. Yeah, you can try to after you assume that they are about the same, then you can set that they are equal to approximately equal to 2wn minus 1 plus 1. Then you can further backward substitution the n minus 2, n minus 3, and keep substitution every loop. Then eventually you will get this 2 power to n minus 3, 2 power to n minus 2. Yeah, this one times 2 Then there's a 2 power to n minus 3 here. Then minus 4, minus 5, and so on and so forth. This is a geometric series. So if you substitute the geometric series formula, you got how many terms? So it's n minus 1 from 2 power to 0, 2 power to 1, 2 power 2 to 2 power to n minus 2. So total you have n minus 1 term. Then every time you times 2. So your r is 2. Your r is 2. A is equal to 1. The first term is 1. So in the end, you got 2 power to n minus 1 minus 1. Okay, this is the approximation solution. Yeah. So you may think about, so I said this thing is not correct last Friday. Not very correct because it's an approximation solution. Is it whether we can get the exact solution? Is it possible? The answer is yes. It's possible to get the exact solution. It's possible to get the exact solution. Yeah, how to do it? Then you need to recall something you learned in discrete mathematics. In discrete mathematics, you have learned that second order linear recurrent with constant coefficients. But I know that you only learn the homogeneous one. So which means your Fn is equal to 0. The Fn is equal to 0. Yeah. So that is the homogeneous one. But my one, this part is homogeneous one is not enough. Because you find that there's 1 over there. If you back to just now the equation, there's a 1 here. There's a 1 here. So that will end up that your second order linear recurrent equation is a non-homogeneous equation. Yeah, that means there are some term which is not same as the recurrent equation. Okay. So how to solve this thing? To solve this thing, you need to find the characteristic equation of this recurrent equation. Yeah. That means this one is your AR square plus BR plus C. This is the characteristic equation of this linear recurrent equation. And then from that, you can find out the root. From the root, you can, then not surprising, there are a few possible scenarios. The first scenario is the root have two real and distinct root. Yeah. And another scenario is when b squared minus 4ac, these portions are equal. That means this portion will be equal to 0. That means you have one double root. You only have one root. Then the third scenario is two distinct complex root. Yeah, that means if your b squared minus 4ac is less than 0, that means this is a complex number. So there are 3 possible scenarios. So different scenario, you have corresponding Yeah, different scenario, you have corresponding homogeneous solution. Okay, so this is the homogeneous solution. That means you consider when equal to 0 part first. This is a homogeneous part. Okay, this I think it should be exactly same as what you learn in discrete mathematics. Okay. So this is a homogeneous solution, and what I would like to highlight is like, for example, you look at this one. Later we are interested is the first case. Yeah, this part actually is formed by a two geometric sequence. The alpha plus this root one actually this is a geometric sequence, and then this one is another geometric sequence. So in short, the homogeneous solution you can think that is a linear combination of two geometric sequence for the first case. For the second case, this is a geometric sequence. This one is a RE geometric. This one is like n, so it's like when n equal to 1 is 1, when n equal to 2 is 2. So it's like r power to 1, then plus 2 r power to 2, and so on and so forth. So you can call it a RE geometric sequence, maybe. Yeah, so it's not same as the first one. Then the third one is a complex geometric sequence. Yeah, I just rewrite it in the form of the trigonometric form, but actually you can just use the first one. It's a similar, it's just the root is a complex conjugate instead of a real root. Yeah. So why? No, that is the characteristic equation. I think you should learn it in your discrete mathematics. Yeah. So when you have this recurrent, actually the characteristic equation is this. Yeah, I'm not saying that this thing is equal to R. I'm saying that is characteristic equation. Okay. Yeah, I think this one you definitely learn it in the discrete mathematics. I have double checked with a few students, all tell me that they have learned it in discrete mathematics. The key is the next one you didn't learn in the discrete mathematics is the next part. Yeah, actually when your right hand side is not equal to 0, that means that is the non-homogeneous equation. In that scenario, your solution not only have a homogeneous solution, but also have a particular solution. So you have two parts. One is a homogeneous. Yeah, so just now we already solved the homogeneous part. So right now I need to solve the particular solution part. In other words, this solution can decompose into two. One is the homogeneous solution. The other one is the particular solution. Okay, so the homogeneous solution is exactly same as what you learn in the discrete mathematics. The particular solution, okay, you need to look at the function. Yeah, so here I only consider one type only. Of course, they can have a lot of things, a lot of possible type. Yeah, but here I only teach you one. That means I only can test you this one, because different function got different solution. So if your function is in this format, then k is a constant. Then there's some geometric sequence, Rpn for the power to n. Yeah, then you need to consider this R, whether this is same as the root in the homogeneous solution. Yeah, if this Rp is not equal to any one of them, then in that scenario, your particular solution definitely is in this format, Arp power to n. Yeah, if your Rp is equal to one of them, one of the root, in that scenario, your particular solution will be Anrp power to n. Then if your characteristic equation, the root of your characteristic equation is a double root, and at the same time this double root is same as your particular, this RP. Then in that scenario, your particular solution is an squared times rp power to n. K is given. All the k and rp power to n is given in the question. Yeah, later you can see what is the k. It's given already. The problem here you don't know is the a. A you don't know. At this moment you don't know. You need to find out. Just like just now the homogeneous solution. The alpha and beta you also don't know. These are three unknown coefficients you need to find out later. Okay, so this is the second order linear non-homogeneous recurrent with constant coefficients. So we go back to just now the question. You have this equation, recurrent equation. Right hand side is a plus. Where got right hand side is a plus b? No. Right hand side cannot be a. How come the right hand side can be a plus b? They are the different. If it's a second order, if it's, yeah, you need to take notes. If it's not the second order, this must be second order, means that you definitely have one Wn and the other one is to be 2 steps away from him. So it's Wn minus 2. Yeah, if you're talking in that way, that means you don't have the middle one. Then your b is equal to 0. Yeah. So it's possible. Yeah. So back to just now the question. The original, yeah, I'm asking the number of function call for this Fibonacci function. You already derive from the algorithm, you already derived the recurrent equation. Yeah, which is this one. I just rearrange it into this format. Then I can easily find out that my A is equal to 1. My B coefficient is negative 1. My C coefficient is negative 1. Okay. Maybe use pen clearer. Okay. This is my A ma. I didn't write anything, means that it's 1. Then this is negative 1. B. C is negative 1 as well. So actually, I can find. So first I trying to solve the homogeneous solution first. Yeah, that one is quite standard. So if you know that your characteristic equation is your A R square, your characteristic equation should be A R and yeah. Let me erase this one. Back to my pen. Minus R minus 1. Because B is negative 1, C is negative 1. Yeah, so this is the characteristic equation. Then the solution, the root of this characteristic equation is minus 1 plus minus square root 5 over 2. Okay, if it's okay, take notes. If this thing is not in the KP, you cannot rewrite it in this format. Yeah, basically the non-homogeneous solution, you may not be able to solve it in that way. I only consider there are a lot of type of function. We only consider one type only here. There are a lot of type. I'm not discuss. Otherwise, this will end up is a mathematics courses already. So I only introduce one only. So you expect that only this type of function we will consider in the test, in the whatever assignment, assessment. Yeah. So the homogeneous part, you don't need to consider this portion. Is homogeneous part is that when this thing is equal to 0. Okay. Then you can find out the corresponding characteristic equation. Once you find out the characteristic equation, you easily find out the root of the characteristic equation. Once you have the root of the characteristic equation, you just need to look at the that three scenario, obviously this is the first case, which has a two distinct real root. Have two distinct real roots. So it's the first case. So in the first case, that means there are two geometric sequence. One is this one. This is another geometric sequence. So it's a linear combination of two. This is exactly same as what you learn in the discrete mathematics. For this one, you expect it's not you assume, it's like you consider you're trying to decompose your solution into two parts. One is the homogeneous part, one is the particular solution. It's not I assume it is zero. More precisely to say, is like I'm trying to decompose the solution into two. One is the homogeneous, one is the non-homogeneous. Then now I'm trying to solve the homogeneous one first. So I let it equal to 0, because later the other part will handle the equal to 1. Yeah, because 0 plus 1 is equal to 1. So after you sum these two, yeah, this one will somehow give you substitute back, this one will give you 0, then this one will give you equal to 1. So the total will be still valid. Yeah. So you follow this characteristic equation, find the root, then you get the solution. So this part, yeah, is the solution. The problem is that you don't know what is the alpha and beta. This thing you need to find out later. So this is two unknown. Yeah. For the particular solution, now I'm trying to talking about particular solution. I need to remove. Okay. So this is the one. Actually, you can somehow rewrite this thing to, because I only teach you one function, which is this thing. I only know how to do this thing. So I need to rewrite this thing in this format. So I'm trying to write this in this format. So my k is, yeah, just now someone asking what is k. So in this question, the k is 1. What is the rp? Rp is also 1. Because whatever things 1 power to n is any integer number greater than 0, then it's always equal to 1. So it's not surprising, this is equal to this. Times. No, times. Not plus. 1 times. I'm trying to write in this form. I'm trying to write this function in this form. Okay? Yeah, you need to find, because you only know, I already simplified this, you only know one function. So definitely whatever things you give you have to find way to make it in that form first. Okay? Yeah, if it's 2, then it's 2 times 1 power to n. No? Okay? So after you have this form, you find that the root rp is not equal to any one of the root here, right? So again, it is the first case. If it is the first case, implied that your solution is arp power to n. Because rp is equal to 1, so not surprising, this is a lah. Because rp is 1, 1 power to n. Yeah, still the same lah. 40, then 40 times 1 power to n more. What's the issue? Yeah. Tutorial have more complex. Another one example, you can go and take a look. So WP is equal to A. Okay. So now you know what is, but your A you still don't know. You need to find out your A. Alpha I also don't know at this moment. Beta I still don't know. So I have the problem. I need to find out what is the alpha, beta, and A. Yeah. What I know that if I substitute this portion back to this equation. Okay, maybe clean the screen first. Okay, so if I substitute this portion in red back to this recurrent equation, I will get 0. So I also implied that if I substitute A back to this equation, this recurrent equation, I will find out this recurrent equation, particular solution, because homogeneous part will give me 0. So particular part definitely give me equal to 1. So in that scenario, I can find out what is the A. Will LP always be 1? No. Case by case. In this particular question, is equal to 1. But other case, yeah, it may not be equal to 1. So I find that A equal to -1. So now A resolve. This thing done. I know it's -1. So alpha and beta. How to find alpha and beta? To do this, you back to the previous slide, you know that W1, you know two base case. W1 is equal to 1. W2 is equal to 1 as well. These two have one function call. So in this scenario, you substitute back your W1 and W2 to this equation. So you can get two equations. Yeah, this one I left for you. Go back and practice to find out the answer. You see, if you have two equations, two unknown, alpha and beta is unknown. Yeah, you substitute back, you've got two linear equations and two unknown. You definitely can solve and find out what is the alpha and beta. So in the end, your alpha is 2 over square root 5. Then beta is -2 over square root 5. Why is it? I substitute particular solution. This one is A, right? Because this WP, this particular solution is a constant sequence. So whatever your n it is, it's always give you the constant A. This one also A. Yeah, all these are A. So A minus A minus A equal to 1. Then, yeah, just rearrange it, calculate it, A equal to -1. That's it. Okay, so in the end, alpha, beta, A, all you can find out. So that is the solution. So in the end, this is the things. You can go and try to verify it. I didn't say -1 become 1 power to n. No such thing. Where got -1 become 1 power to n? Okay, so you can go back and verify this. You can try. Yeah, when n equal to 1, you substitute back to this equation, you find that you get 1. You substitute 2, you get 2. You get 1. You substitute 3, you get 3. Substitute 4, you get 5. 1, 2, 3, 4, 5. You expect 5. Yeah. So how to get this equation? This one back to square 1 here. You got one function. Yeah. When you W4, yeah, you recursive call. This is the number of recursive call here and number of recursive call here. So it's this one plus itself. One function call. So total in Wn, how many function call are there? It's this one plus this one plus this one. Yeah. That's how I get the recurrent equation. Yeah, because the question asks you how many function call are there. Okay. So I suggest you can open an Excel, then trying to do this, substitute different n, you can get the answer and see whether it's correct or not. You also can draw out the recurrent function, the recursive call in the tree form. You can find out that that is the answer. In short, you can think that this is two geometric sequence. Yeah, formed by two geometric sequence. Okay. And you'll find that this part actually is a negative. This thing is a negative number. So your power to n, something less than 1. This is 0.618. I think it's negative 0.618. So as your n going bigger and bigger and bigger and bigger, actually this portion will close to 0. Close to 0. When your n is very large, eventually it's dominated by this part. So you find that actually this thing is a function of 1.618 power to n. Of course, not exactly equal to this, approximately. Yeah, when n very large, when n is very large, I have to emphasize n very large. Yeah, so why I want to show you this thing is because you back to just now the approximation solution. That one is 2 power to n. This one is 1.618 power to n. So you can see the difference. Yeah, actually the approximation solution is not very accurate. Okay. So that is what you're supposed to learn in analysis the time complexity of recursive function. Okay, we cover 3 method of forward substitution, method of backward substitution, and this second order linear recurrent. Okay, make sure you know all of them. For different recursive algorithm, you need to use different method. So this is the things I have to discuss. Okay, have to move on to next topic. Oh, sorry. Yeah. Correct. So you can see that actually we're not really interested the constant or the multiplier. A lot of time when your n is getting bigger and bigger, we interest is like whether this is a linear function. Like just now the Fibonacci is an exponential function. We just need to know that whether it is an exponential function, whether it is a logarithmic function, is basically sufficient to get the idea whether this is a good algorithm or bad algorithm. So in this part, we trying to see how the order of growth of different time complexity function affect, and then what is the impact between the faster algorithm and faster computer. So you will find that earlier I think a lot of students are asking why this thing only one C1, C2. Actually, I'm not focused so much about the C1, C2 exactly. I didn't look at every single primitive operation and then define it as a C1, C2. Sometimes the algorithm is very abstract. If you really go into implementation level, a lot of details, then everything's, if you consider as a constant, then your complexity will become very complicated with full of the constant number. And soon you will find that when your n is your problem size n getting bigger and bigger, this constant number can be ignored because they are negligible, because n will dominate the whole time complexity when your n getting very large, in million, in 100 millions. So normally those constant are not significant. Later you will find that we not go focus on analyze how many constant are there here and there. We just simply said this part is a constant, because it's just run a for loop. Inside how you run it, you don't go into details. You're just saying that every iteration you do fixed number of primitive operation, and this part is independent to the problem size. You every iteration you run one times, you need to cost you so much operation. The problem is the number of iteration cost related to your problem size, and that is the things we need to concern about. So the constant time normally is not significant, and the multiplier are not important. Later you will see the example. Not important doesn't mean you can simply ignore, but is when we're talking about order of growth, we will consider those linear function are in the same category. But we not further we won't because you compare a linear function and a logarithmic function, for example. Logarithmic function definitely grow much slower regardless what the multiplier is, because you have a very large multiplier, logarithmic function, and a very small multiplier, linear function. You find that in the end, the linear function, when your n going larger and larger, the multiplier is not the raw decide the growth. It's the order of growth, is the linear function or logarithmic function decide which one is better, which one grow faster, which one grows slower. So I think earlier we have when we have a fixed, when we define it as a constant, it's operation. Yeah, so we constant is the number of iteration. So in this case, you always run some declaration assignment to run this double for loop. Yeah, then there's some constant A. Not surprising, there's some constant A. Then in this one, always you run fixed number of operation. Yeah, it costs you B time complexity is B. But the key is this is the n square because it's a double for loop. Yeah, you start from 1 to n, then your j is equal to 1 to n. Not surprising, you need to run n square number of B operation. Yeah, then you find that your n getting bigger and bigger. The A is not important, it's negligible. This part is very small. Relative, you have a very large n. Yeah, so you can expect this is a quadratic function. So that is something we would like to know. Yeah, instead of analyze, is it A or A plus A or 2A or 1A? Yeah, that is not that critical. The critical part is the n square. Okay, when we analyze the order of growth in time complexity. Okay, maybe try have some example. Let's say you have 6 algorithms here. The first one is a linear operation. It takes 13n microsecond. The second one is the linear logarithmic, n times log n. So this is a linear logarithmic function. Then the third one is a quadratic function. The fourth one and the fifth one, these 3 are quadratic function. The last one is the exponential function. Okay, these are their corresponding operation in microsecond. So let's say I substitute n equal to 10. Yeah, I need to take so much time. 0.00, very small number in second. Then when I increase 10 times, not surprising, this thing is a linear function. So the operation times, the computation times will increase 10 times as well. Yeah, I increase another 100 times, it grows 100 times. Yeah, similarly to this. So this is you can see that the computational time is linearly increased. If you look at the second one, it's a linear logarithmic. So you can see that it will grow. It's not just in term compared to the first algorithm, it's just not simply higher. You can see that the growth is a little bit faster. Right? When this thing is 10 power to 6, especially your n getting bigger and bigger, you can see very obvious the difference. Yeah. But in the starting is maybe about the same because your n is small. When your n getting bigger, this linear logarithmic playing the role. So you can see the difference. Compare 13 and 256. Okay, compare in the starting it's only 0.0013 and 0.0043. Yeah, the changes, because it's a logarithmic, there's a n times logarithmic, definitely you got one more, that means you will grow a little bit more faster than n. But the next one will go much faster because it's n square. Yeah, so you can see the growth. Yeah, this one is you increase 10 times, actually your computational times increase 10 times. You increase 10 times, it increase 100 times. No, should be 1,000. Then you increase 10 times, you square it. You increase 10 times, you square it, then you increase 10,000 times. So right. Yeah. So n square, because it's n square. So not surprising when your n power 10 power to 6, it grow to 150 days to get the result. Yeah. Similarly, when these two, the algorithm 4 and 5 have similar scenario. Just of course, is this one definitely grow faster than algorithm 3. But you can see that the relationship is still in parallel. This thing grow faster, this one also grow faster. Yeah, because it's just the multiplier is 10 times bigger than the algorithm 3. Yeah, later you from the graph you can see you have a better picture about this thing. Yeah, similarly this one you just add some constant. It's not much different compared to the algorithm 3. It's just a little bit higher only. But when your n is big enough, this 100 is negligible. Yeah. Then the last case is a exponential function. Yeah, you can see that when your n just increase 10 times, basically you have no chance to see the result, because maybe your grandson also have no chance to see it. Yeah, it's 4 times 10 power to 16 years to get the result. Yeah, that is crazy. Yeah, so that's why we normally don't really like something 2 power to n. Okay, so if you back to overall, maybe from the chart will give you a better picture. So you can see that if it's a logarithmic function, yeah, actually your n grow very fast, 10 times. Yeah, the computation times grow very slow. But when you use a linear, it's a linearly grow. Then you can see when you have 13n square and 13n square plus 100, yeah, it's almost the same. Okay. Then one thing I want to highlight is this 130n square and 13n square. Yeah, you can see that actually when your n getting bigger and bigger, these two lines is almost parallel. Yeah, that is what the meanings of multiplier is not important here. Okay, so overall, among all these functions, yeah, you will find that n factorial is the one grows fastest, followed by the exponential. Because exponential is just 2 times 2 times 2. This one is like 1 times 2 times 3 times 4 times 6. Yeah, after a while you can see about less than 10 you already cross and become the faster one. Then this one and this one linear. Yeah, then the slowest one among this function is 13 log n. The logarithmic function is the one slowest one. Yeah. Then 10 power to 2 can be ignored. This is referred to this one. Yeah, because you can see almost starting you can see the difference. This blue color one and the green color one. Starting you can see the difference. Yeah, but after your n dominate the whole function, actually this 10 power to, yeah, this 100 is negligible. Can ignore. There's not much different compared to n square. Yeah. Then, yeah, when I said 13n square and 130n square, yeah, they have similar growth. It's when your n getting bigger, these two lines is almost parallel. Although 130n square still grow a little bit faster. But yeah, you can categorize them as the same growth function. Yeah. So that is the meaning here. Oh, yeah. Then maybe people trying to think that they are rich, they can buy a very expensive computer 10 times faster than what you have now. Yeah. Is it better to have a faster computer or have a faster algorithm? Yeah, I think the answer is quite obvious. Yeah, sometimes, yeah. So the problem sides are not maybe you have a, yeah, maybe let's say we have I only left 3 minutes. Okay, so let's say you have a old computer, yeah, which 1 hour can do 10,000 basic operation. And I'm trying to get a very expensive 10 times faster computer, which can do 100,000 operation per hour. Yeah, then we see which one we use the same, compare with the same algorithm, see whether is it good to have a 10 times faster or 10 times faster or better or have a better algorithm. Okay, if all, yeah, so we're trying to analyze all computers solve a problem of size n in 1 hour. What is the largest size, largest problem the new computer can solve in 1 hour? Okay, let's say we're talking about a linear function. Yeah, then maybe I show you the table. Yeah, let's say you have a linear function. Okay, this n is the largest problem size solved by the old computer in 1 hour. That means 1 hour he can operate 10,000 operation. So this one is the new computer which can operate 100,000 operation in 1 hour. So let's see, when your algorithm is 10n, is a linear function. Yeah, this one can operate 10,000 per hour. So he can operate your problem size can be 1,000. He can finish it in 1 hour. Then your new computer can handle 10,000 data. So it take 1 hour to finish it. So compare this one, improve 10 times. Yeah. So if you have a linear problem, okay, you can buy a 10 times faster computer. It can help you to improve 10 times. But when I have, similarly, 20n also same thing. If the old computer can operate only 500, N500, and then do it in 1 hour, 10,000. Yeah. So the new computer can handle 5,000. They can do the problem size of 5,000 in 1 hour. And the improvement also 10 times. But if you have a problem is the linear logarithmic, yeah, you find that this thing not really improve 10 times. You only improve 7 times. If you have a square one, actually you only improve 3 times. If you have an exponential one, yeah, it's basically negligible. The difference, yeah, one is 13, one is 16. It's nearly no big difference. Although you already improve your computer power to 10 times, the improvement is nearly nothing. Yeah. So that, in short, trying to show you that if you have a very bad algorithm, even you buy 10 times of faster computer, you still cannot resolve the problem. Compare, you improve the algorithm from exponential to linear. That improvement is a lot more significant than you buy a 10 times, 100 times, 1,000 times powerful computer. And that cost is very scary. Yeah. So maybe I have to stop here. This thing I will carry on Friday. Yeah. And the asymptotics time complexity analysis, yeah, will be done on this Friday. Similarly, this one, yeah, is also the things. Maybe I will talk again on Friday section. Okay. Yeah. Okay. Thank you. Any question? Yeah, today attendance is quite low. Only 170. Okay. If not, I will stop to get the A minus A. Well, back to just now this one. Okay, this part I think you have no problem. How to get the A minus A? Yeah, so here I already mentioned just now, this part is the, let me do one more times. This part is the W homogeneous part. So if you substitute the homogeneous part back to this equation, what will you get? 0, right? Your right hand, yeah, this thing you substitute back WH minus WHN minus WHN minus 1 minus WHN. This is how you get this alpha beta because you consider the homogeneous equation. So this thing definitely equal to 0. So where did this one come from? This one definitely come from the particular solution. That means it's WP n minus WP n minus 1 minus WP n minus 2, because this equation plus this equation will be equal to these two, you plus, you will get this thing. So substitute back this one. What is the WPN? WPN is equal to A. What is the WPN minus 1? It's still A. Of course, because this particular solution tell you that this sequence is a constant all the times, regardless your A, regardless your N. Yeah, your N is whatever number. N equal to 1 is equal to A. N equal to 2 is still equal to A. N equal to 3 is still equal to A. N equal to 4 is equal to A. It's just you don't know what is A. So you just substitute back all equal to 1. A then equal to 1. A minus A minus A. So you get minus A equal to 1. So A is negative 1. Negative 1. So it's trying to tell you that actually this particular solution is a negative 1 sequence. So that's in this sequence, when n equal to 1 is negative 1. When n equal to 2 is still negative 1. N equal to 3 still negative 1. N equal to 4 still negative 1. N equal to 5 still negative 1. All the times. Okay? If not, okay, no problem. I will stop today's streaming. If you still have any question, just send me an email. Okay? Goodbye.